Good morning, everyone. We'll pick back up here in chapter 11. So we had ended on this question here where we were trying to figure out which molecule below has the greatest boiling point. What we're trying to figure out is which molecule has the strongest intermolecular forces, because having stronger forces will increase that boiling point. And so having the hydroxyl group, like water, has a higher boiling point than NH3, so water's has stronger intermolecular forces than NH3, then we're going to prefer to have, for stronger intermolecular forces, the alcohol instead of the NH2 group. And then having a long chain is good because that's going to add to the dispersion forces. So having a long chain of carbon atoms can help have more dispersion forces. And then we saw that having a longer chain of carbon atoms was better than having a branched chain. So having a longer chain linear of carbon atoms connected, where these carbon atoms are just connected one after the other, that's better than having this like branched chain. So if we have this molecule here, it would look something like this. And having this branch point doesn't allow those methyl or the carbon chains to get as close together. If you imagine adjacent molecules, we have this straight chain, you get much more interaction, you get much more of an ability of those chains to be able to induce the dipole moment in the other to increase their attractive forces. So we get more dispersion forces with the longer chain, making the hydroxyl group, but with the longer chain of linear connected atoms, have the higher boiling point. If we made the chain longer, if we added an extra CH2 group, we're going to keep increasing the boiling point. So if we were to just add another CH2, this one here is the 1, 2, 3, 4, 5, that's pentanol. If we go to hexanol, hexanol should have a higher boiling point than pentanol, heptanol even higher. So if we keep increasing the length of the carbon chain, we're just adding to those dispersion forces. Doing so with those atoms connected in a linear fashion is better than the branched fashion. Okay, let's look at the next question. Which substance below can only exhibit dispersion forces of attraction, meaning which molecule only has the dispersion force and does not have the dipole-dipole force or hydrogen bonding forces of attraction? Okay, so why don't you guys give this one a thought for a minute or two to think which molecule only exhibits the dispersion force of attraction? All right, so if you were thinking on this one here, what we really want to address is which of the molecules are polar, which are non-polar. HBr for sure is polar. We have bromine is relatively electronegative, hydrogen's not, so we're going to get a good difference of electronegativity here. And so we're definitely going to have a built-in set of charges for HBr. That's going to give it the dipole-dipole force of attraction. Still wouldn't have the hydrogen bonding force of attraction. We need H directly bonded to NO or F. to have the hydrogen bonding force of attraction, but we would have the dipole-dipole force and dispersion forces for HBr, so 2 would not be the answer to the question. 3 is a good answer because hydrocarbons don't have a big difference of electronegativity between carbon and hydrogen, and then also you end up with lots of cases where the dipoles are canceling each other out anyways. So we end up with nonpolar compounds for things like hydrocarbons. If we also had a molecule like CCl4, this would be another example of something that would be nonpolar. So anything that's nonpolar would only have the dispersion force of attraction. And so then if we look at CH2Cl2, we have to remember we have a tetrahedral molecule, we have 4 domains about carbon, we have chlorines about 109.5 degrees relative to each other. They're not opposed by chlorines on the opposite end of the molecule, so we have a polar molecule. Now, one thing to go back to, if we were looking at this Lewis structure here, if we were sketching the Lewis structure, came up with this structure, we have to make sure to go to the molecular geometry. This is a question on the test that actually was missed by a good number of students is this molecule polar or nonpolar? And it's polar. And you have to remember, if you're looking at the Lewis structure, you have to consider the molecular shape, the molecular geometry. And so polar molecule for CH2Cl2, meaning it also has the dipole-dipole force of attraction. So only 3 here would have the, so only the C6H14 would have the dispersion force of attraction. Now, only having dispersion force of attraction doesn't necessarily mean that the intermolecular force can't be strong. C6H14 hexane is actually a liquid at room temperature. So if you have a big enough molecule, enough atoms on the molecule to distribute those electrons, then you can actually have a still relatively strong set of attractive forces between the molecule. So if we were to compare a relatively small polar molecule to a relatively big nonpolar molecule, you'd have a hard time predicting which one has the higher boiling point. But remember, if we're comparing molecules that are of comparable molecular weight, if you're comparing a molecule that's 100 AMU but polar versus 100 AMU nonpolar, probably you would expect the polar molecule to have the higher dipole moment. So if we're predicting trends, we want to pick similar size molecules to make a good comparison. Okay, so there's a few properties we want to show how they connect to intermolecular forces. One of those is viscosity. Viscosity is a measure of the resistance to flow. So something that resists flowing is something that's like thicker, like think molasses or honey. Something that has a thicker consistency with the liquid is something that would be more viscous. And so if you compare the viscosities of hexane to heptane to octane, nonane, decane, where we're imagining as you go down this series that we're increasing the intermolecular force strength because we're increasing the size of the molecule, getting a greater dispersion force, then we see the viscosity is increasing with the same trend. So viscosity is increasing as we increase the intermolecular force strength. And this should, I think, make a fair bit of sense that as a molecule is becoming more attracted to itself, it's going to resist flowing. So something like a molasses is a longer chain molecule that actually has a lot of hydroxyl hydrogen bonding groups attached to it. And so the longer the chain of the molecule, the more you're going to get this resistance to flowing. So strengthening intermolecular forces increases the resistance to flow, increases the viscosity. Another property is surface tension and capillary action. And so you probably know and have seen many times the water meniscus in a test tube. And so you get this upward meniscus because the water molecules have a mutual attractive force with the silicates in the glass. And so if you have a mutual attractive force, the molecules in the water are attracted to and have a attractive force with water, so that gives the water molecules what we call a gives it a capillary action. So a capillary action is the idea that, say, a plant stem, water has an attractive force at the plant stem that allows the water to travel up the plant stem. And so the question usually becomes, or is a matter of, is the force with the glass stronger or comparable to that with water, then you get the upward meniscus. If you take something like mercury in a test tube, you actually get a downward meniscus. You get a downward meniscus because you actually get repulsion. And so we see attractive forces between water and glass, and we see repulsive forces between mercury and the glass. And so if you get repulsive forces, then the mercury atoms are trying to stick more together. They're trying to repel the glass, so you get the downward meniscus. And so you get the opposite of capillary action with something like mercury in a test tube. Then we also have the concept of surface tension, that surface tension is a measure of how much energy it takes to break the surface of a liquid. And so the stronger the intermolecular force is, then the more energy has to be given to a surface to break it. So water actually has a relatively strong, high energy to break its surface. That's why bugs and things can walk on the surface of water, because it takes a fair bit of energy to break the surface of water. So surface tension and capillary action, these two properties here, are directly proportional to strengths of intermolecular forces. So if you increase the strength of the intermolecular force between the liquid and the glass, or whatever the item is that the liquid's attracted to, then you're going to get a stronger capillary action. If you reduce the intermolecular force, if you weaken it or make it repulsive, then you're going to get the downward force. You're going to get the opposite of capillary action. And then if you have a different liquid that has a stronger set of intermolecular forces, more energy would be required to break the surface of the water. So you'll have a higher surface tension with a stronger intermolecular force. Okay, so we can have a summary of how intermolecular forces affect some of the key properties of substances. So melting point and boiling point, these are certainly going to be directly proportional to strengths of intermolecular forces. Increase intermolecular forces, you increase melting points, you increase boiling points due to those increased interactions. And we see the same thing for viscosity, surface tension, capillary action, that if you strengthen intermolecular forces, increase those, then we're going to increase those properties as well. So we get the direct relationship between strengthening intermolecular forces and the key properties of things like melting point, boiling point, resistance to flow, energy to break a surface, and then the action of a liquid up a plant stem or test tube. So a couple other properties we're going to look at are things like the enthalpies of phase changes, so enthalpies of vaporization, fusion, sublimation. We're going to see that these are also going to be directly proportional to strengths of intermolecular forces. If you imagine like the enthalpy of vaporization, what this would look like is the enthalpy, say, of liquid water going to gaseous water, that the delta H of this process, or the delta H of vaporization, is what this is showing. The liquid to gas is the vaporization change. So an enthalpy of vaporization is going to be directly proportional to strengths of intermolecular forces, meaning the stronger the intermolecular force, the higher the enthalpy of vaporization should be. So if we can change water to a different substance that has stronger intermolecular forces, we would predict that that enthalpy of vaporization should increase. And then we'll see one other property, that being the vapor pressure. This is going to be the one that goes inverse, that as we weaken intermolecular forces, and we're going to strengthen vapor pressure or increase vapor pressure. So we'll talk about vapor pressure in a minute, but just the thought would be, if you had a substance that had a really strong force of attraction, you would expect to find very few vapors above that substance. If you had another substance that had a really weak set of attractive forces, you might expect there to be more vapors of that substance above the liquid. And so if you imagine something like say gas, which has mostly nonpolar compounds in it. So if you're filling your car with gasoline, you usually smell the gas because those compounds have a relatively weaker force of attraction, so they have a higher vapor pressure. That's what you're smelling. If you have a liquid, like water or something, maybe you don't notice as much vapors above that liquid because it has a stronger intermolecular force. So the stronger the intermolecular force, the lower the vapor pressure, and we'll talk about that as we continue. Okay, so let's look at some phase change values here. So this is just showing us a phase change for a solid having to absorb heat to melt into the liquid phase. So I think we remember that the melting process is endothermic. So going upward here is endothermic. And then coming back down would be exothermic. So solid to liquid, endothermic, heat has to be absorbed. If we go liquid and freeze back to the solid, then that would be an exothermic phase change. Heat would have to be released by the liquid to freeze into the solid. And so we have our melting transition. And then we also have our vaporization transition from liquid to the gas state. Now, if you notice, the vaporization enthalpy is a fair bit bigger in this diagram, where it looks like it's a larger magnitude than the melting transition. And this can be explained by the fact that to melt a substance, we have to break some of the attractive forces. So we're not breaking all the intermolecular forces, but we're breaking some of them. We're taking a substance that was kind of frozen and then making it liquid, but where the particles are still near each other, still experiencing some of their intermolecular forces, just not all of them that they're experiencing in the solid phase. And then to vaporize, to go to the gas state, or if you imagine being an ideal gas of non-interacting particles, the idea would be we're going from a substance with some intermolecular forces to a substance with effectively no intermolecular forces. So here we have to break all of the remaining intermolecular forces. And so breaking the remaining intermolecular forces takes a fair bit more amount of energy than it took to melt the substance. So the enthalpy change of vaporization is usually a little bit higher in magnitude than the melting phase change enthalpy. But then if you just use the simple law of thermodynamics, the first law of thermodynamics, if you go from solid to liquid, liquid to gas, if you add those two phase changes together, then we're going to get the sublimation phase change. So if we take our delta H of fusion, the enthalpy to melt a substance, plus the delta H of vaporization, then that's going to equal our delta H of sublimation. So it's just saying solid to liquid, and then liquid to gas, that those phase changes will equal the solid to gas. So the sublimation enthalpy just being the sum of those two phase change enthalpies. So the next slide will compare some different substances, enthalpies of vaporization and fusion. So for example, butane's hydrocarbon only has a dispersive force of attraction, so doesn't have a very strong intermolecular force, has a relatively low heat of fusion, so it doesn't take much heat to melt the substance. Takes a fair bit more, but still relatively lower here on the chart for its heat of vaporization. And then the two summed together would be the heat of sublimation. So if we compare to diethyl ether, where we put an oxygen in between two like ethyl chains, we make a slightly larger molecule, but one that can have some dipole-dipole force of attraction in addition to the dispersion force. And so then for diethyl ether, we see a little bit higher heat of fusion, a little bit higher heat of vaporization, and then of course the two being summed together being the heat of sublimation. Water doesn't take that much heat to melt the substance, but it takes a fair bit more heat to vaporize the substance because we're breaking then all of the remaining intermolecular forces. And so water having the H bonding force of attraction. The one thing water does lose is some of the dispersive forces that we had on these relatively longer chain atoms here. It would be slightly more interesting to compare something like diethyl ether to a longer chain alcohol. So if you compare to a comparable molecular weight, like pentanol or something, like pentanol would have actually a lot higher of a boiling point than water, a lot higher of a phase change for its vaporization, probably also a higher phase change for its melting. But water is now a smaller molecule. It's kind of hard to start comparing small molecule that hydrogen bonds with big molecule that has dispersion forces and dipole-dipole forces. But water has all three, just to make sure that we're clear on this, that water has H bonding, dipole-dipole forces, and dispersion forces. Diethyl ether has dispersion forces and on top of the dipole-dipole force. And then butane only has a dispersion force of attraction. Now mercury is a little interesting in that it's a metal, it has metallic bonding. So mercury is also a liquid at room temperature, but it can be frozen. Does take some heat to melt solid mercury, and then we can boil mercury. Don't recommend it because mercury vapor is very toxic. But if you boil mercury, it has a phase change of 58 kJs per mole. But this is relatively comparable for probably the closest substance in terms of phase change for the fusion and then vaporization being relatively close together. Most substances like water, fair bit of differences, a little bit of heat to melt, a lot more heat to vaporize. Some of the two, of course, still being the heat of fusion. or the heat of sublimation, I mean. And so mercury here just has our metallic forces of attractions. So we don't talk too much about metallic bonding here in this chapter, but mercury here would have that metallic bonding, but just showing its heat of fusion, vaporization, and sublimation. Metallic bonding is a very strong force of attraction, so you see those phase changes are quite high. Back real quick. 41. Now this diagram here is showing us sort of like a heating curve of trying to understand if you have a substance at a low temperature that's a solid, imagining perhaps water. So if you imagine at minus 25 degrees C, we have frozen water, that if water is going to reach its melting point at 0 degrees C, that it's going to have to absorb some heat to go from minus 25 to 0. The heat that it has to absorb would be related to the specific heat of ice. And you might recall in chapter 5 when we were talking about specific heats that we said different substances in different phases have different heat capacities. So the heat capacity or the specific heat of ice will be a little bit different for solid ice compared to liquid ice. But we would just have, if we wanted to know for a certain sample of water how much heat it has to absorb to reach its melting point, we would use the specific heat. But then to get through the melting point, to actually go from the solid to liquid, this now depends on the delta H of fusion, the enthalpy it takes to melt the substance. And so for water, this turns out to be about 6.01 kJs per mole. So for every mole of water that we have, 6.01 kilojoules of energy would have to be absorbed for the solid water to turn into liquid water. But then we would still be going from 0 degree water to 0 degree water, but we would just be going through the phase change. So as a substance melts, as you go through a phase change, you just go from having 0 degree ice to 0 degree liquid water, but still being 0 degrees on either side of that phase change. Something you'll do a lot in organic chemistry is you'll synthesize or you'll prepare like a solid, and you'll actually test its purity by looking at its melting point and seeing how wide of a range a melting point is. Because a melting point for a pure substance should be literally at one degree. Like at whatever the melting point temperature is, you should see that transition take place. As you have a sample that's more impure, you start to see it melt at one temperature, then the temperature will rise as it's changing its phase. So for pure substances, you get this really nice transition at the same temperature, 0 degrees to 0 degrees, ice to liquid water. And then if we were to go from 0 to 100, this would just rely then on the specific heat of liquid water, getting through the vaporization. If we want to go from water liquid to water gas, this is our delta H of vaporization. You don't have to memorize this, but this is about 44.0 kJs per mole for water. Actually, it was on the previous slide. I forget what it was now on the other one. So it's about 41 kJs per mole. Again, not something you have to memorize, but just trying to get the magnitude of thinking of how much energy water has to absorb. It's about 41 kJs per mole of water have to be absorbed for it to go from a liquid into a gas. And then you could keep heating water. And then the specific heat of gaseous water for steam, it would have a different heat capacity, but if we knew the heat capacity, we could calculate the heat it would take to turn water into steam. Now, I can tell you that, in the past, I would actually go through an example to say, if you have 100 grams of ice, how much heat does it have to absorb to turn into 100 grams of steam at some temperature? And it just becomes a laborious task of kind of going through each of these different calculations of how much heat to change the temperature, how much heat to get through a phase change, how much heat to change the temperature again. And it's really not that exciting of a problem. So I'm going to go ahead and not do one of those problems, and we're not probably going to see anything like that in the test anyways. It becomes a long problem and just becomes an exercise in futility more than a useful problem to look at. But you can probably imagine trying to figure out how much heat it takes to go through a phase change. But one of the keys is that this is the phase change here that takes the most energy. Getting through the liquid to gas phase change is the one that takes the longest. In fact, I think we know this. Like if you're if you were to put like a pot of ice on the stove and try to turn it in and boil it, it probably would take a fair amount of time to melt, but then it would take a lot longer for the entire pot to eventually boil. So it takes a while for a pot of water to get to its boiling point, and then imagine how much longer you have to sit there for the whole pot to go dry. That would take a lot of time. The reason why it would take a lot of time is a lot of heat has to be absorbed in order to vaporize the substance. So it takes a fair amount of heat to get to the boiling point. That's when we start to see boiling water, and we can go on with cooking our spaghetti or whatever. But if you want to completely vaporize an entire portion of water, you're going to be sitting waiting for the liquid to gas phase change process, because that's the one you can see in the diagram here that takes a majority of the heat. So you can almost like look at the fraction of heat here, that about 75% of the heat on way from ice to steam is just the liquid to gas phase change transition. Okay, so we'll forego playing with the numbers here and just keep that conceptual. And so for vapor pressure again is the pressure above a liquid. Probably one of the obvious times that I experience vapor pressure, and you guys might too, is if you have like a coffee mug like this. Not exactly, this isn't obviously a coffee mug. But you have one of those nice ceiling coffee mugs, and you fill it with coffee, and maybe you put some sugar or cream, whatever you like, in it, and you shake it up, and it's hot, and then you release the pressure. It like hisses, and it hisses because water at temperature near its boiling point has a relatively high vapor pressure, and when you put it into a container and then you seal it up, that's what we're showing here, is if you take ethanol, put it into a container, and then you seal the container is initially at atmospheric pressure. So we initially have atmospheric pressure inside of our container. And so then eventually ethanol molecules are going to escape into their gaseous state, and we're going to have a pressure above atmospheric pressure. That would be the example of the coffee mug. We put hot water in here. The pressure above the liquid is just air, just standard atmospheric pressure. We seal it up, shake it up, and then the pressure increases because gaseous particles are escaping into the gaseous part of our container. We release the pressure, we hear the hiss from the increase of pressure. This container here is actually evacuated, where we had effectively no pressure or a low pressure from evacuation. We fill with ethanol, and then we get to a pressure here that is equal to our vapor pressure. So liquid ethanol in the container has particles that can escape into the gas phase, just as a dependence on the property of ethanol at the temperature at which the sample's at. And so most liquids at a given temperature have a particular vapor pressure. What that means is there's so much pressure of molecules that will escape into the gas phase, and those particles start flying around the container. Some of them will fly back into the liquid phase as other molecules escape, and you start to reach a point where you reach what we call equilibrium. You'll talk a lot about equilibrium in Chem 1220, but you reach a point where the rate of molecules re-entering the liquid phase equals the rate of molecules escaping into the gas phase. And you have then a constant pressure that we call the vapor pressure for the liquid. Now you could probably appreciate that if you have this vapor pressure and you determine whatever it happens to be, let's say it's 20 millimeters of mercury, let's say 20 torr. If you imagine increasing the temperature, so if we increase the temperature of the sample, what do you think happens to the vapor pressure? We probably give more energy for molecules to escape into their vapor phase. We're going to increase the vapor pressure. So temperature has a big link to vapor pressure. As you increase the temperature of a sample, you're going to increase its vapor pressure. And so one way of thinking of vapor pressure is just by thinking as we go to higher temperatures, we're increasing the velocity distribution on average for our sample. And then there's going to be some minimum energy that's required to escape the surface. Remember, this is kind of the definition of surface tension in a way. So our surface tension was the idea that there's some energy it takes to break the liquid surface. Well, there's some minimum energy it takes to have a molecule escape into the gas phase. And so that's temperature independent. There's just some energy it takes given for the liquid for molecules to escape into the gas phase. So if you increase the temperature, you're just increasing the percentage of the molecules that have enough energy to escape into their gaseous form. And so as you increase temperature, again, you would predict that the vapor pressure would increase. So higher temperature for our sample should equate to a higher vapor pressure. So this curve here is showing us some different vapor pressures versus temperatures for some different substances. Let's actually start with water, because we obviously encounter water a lot more. All right, here we go. So hopefully I don't bump this again. All right, so for water has a, at about 0 degrees C, ice doesn't have much of a vapor pressure. Then at 100 degrees C, something happens. So at 100 degrees C, we know the boiling point of water. Well, why do we reach the boiling point of water at 100 degrees C? Well, at 100 degrees C is the point at which water has a vapor pressure of 760 millimeters of mercury. So you reach a point where you have a pressure applied to a liquid by the atmosphere, which standard atmospheric pressure is 760 millimeters of mercury. If you imagine that becomes the vapor pressure of the liquid is like the pressure holding the liquid together. If you reach a point where the vapor pressure of the liquid is equal to atmospheric pressure, well, what's holding the liquid in place? Nothing now, and the liquid will boil. And so a boiling point is defined to be the point at which a liquid has the same pressure as its atmosphere. So a boiling point, so we often call this normal. The normal boiling point is the point at which the liquid has a vapor pressure equal to standard atmospheric pressure. So the point or temperature where a liquid has a vapor pressure of the standard atmospheric pressure is when it's going to boil. And so for liquid water, 100 degrees C has a vapor pressure of 760 millimeters of mercury. And so then if you imagine, compared to water, if you can weaken the intermolecular force, so if we go to perhaps ethanol has a boiling point of 78 degrees C. So you'd imagine if the boiling point goes from 100 to 78, we probably weaken the intermolecular force. You're going to then reach 760 millimeters of mercury at 78.3 degrees C. So we're reaching that standard atmospheric pressure at a lower temperature for something like ethanol. Perhaps we're doing that because we're going from having 2 hydrogen bonds just to 1 hydrogen bond. So we're going from having the ability of water to form 2 hydrogen bonds versus ethanol just has the ability to form 1 hydrogen bond. Interestingly, if you go to methanol, methanol's boiling point is about 64 degrees C. If you keep adding to the ethyl chain, you start to increase the temperature. So once we get to propanol, we're at about, I think propanol's boiling point's about 98 degrees C. So if you go to methanol, boiling point 64 degrees C, and then propanol is about 98 degrees C. Just to give you a sense of how that ethyl chain's impacting boiling point. So for each ethyl chain that we add, we're adding about 15 or so to 20 degrees C of temperature to the boiling point due to the increased dispersion force. And so anyways, for ethanol, lower boiling point equates to a lower temperature at which we're reaching that vapor pressure 760 millimeters of mercury. And so then if you go to an even weaker intermolecular force, diethyl ether, only having the dipole-dipole force of attraction, it has a boiling point that's lower, about 35 degrees C. So at 35 degrees C for diethyl ether, we're reaching that standard atmospheric pressure of 760 torr. And so vapor pressure, you can see here, has an inverse relationship. So we're increasing the vapor pressure by weakening the intermolecular force. So vapor pressure, as we mentioned earlier, then is inversely related to strengths of intermolecular forces. So if you weaken the intermolecular force, we're strengthening and increasing that vapor pressure as a result. So now how can you change boiling point? Like, we can't change the normal boiling point because that by definition is the temperature at which at standard atmospheric pressure a substance boils. But we can change the actual boiling point by changing the pressure. And so the things you can do If you want to boil, like let's say you want to boil water, but not at 100 degrees C, what do? Well, you connect it to like a vacuum chamber. So you pull a vacuum on water. If you reduce the pressure, let's say down to 200 millimeters of mercury, then water is going to boil at a temperature closer to about 70 degrees C, a little bit below 70 degrees C. So you can change your boiling point if you set your atmospheric pressure or through the use of like a vacuum pump. So if we create a vacuum, then our boiling points will change accordingly. Ethanol becomes lower, ethanol boils around 50 degrees C, and then about 0 degrees C, we would have the diethyl ether boiling. Now, there's one other substance on the chart that's ethylene glycol. Ethylene glycol is a derivative of ethanol, but where we add a second hydroxyl group. So ethylene glycol is a molecule that looks like ethanol, but where we have that hydroxyl group on both the first and second carbon. So we add like a second hydroxyl group, and that really increases the intermolecular forces because now we have that second hydrogen bonding source on the molecule, and we also benefit by having that sort of chain of dispersion force to ethyl chains. And so we're going to increase our attractive force, we're going to decrease the vapor pressure as a result. So increasing the intermolecular force is decreasing the vapor pressure. Ethylene glycol boils at a temperature of about, I think, 200 degrees C, somewhere in that ballpark. So a lot higher of a boiling point here, a lot lower of a vapor pressure as a result. So higher boiling point, lower vapor pressure. Now, another thing you can do to change boiling point would be to increase the pressure. So you can increase the pressure by maybe using something like a pressure cooker or an Instant Pot, or have become popular. An Instant Pot is really just a pressure cooker. Now, how this works is if you increase and add to the pressure of a gas sample, then you're going to increase the boiling point. So if we can somehow make the pressure about 1,000 millimeters of mercury, then we would increase the boiling point of water to be about 110 degrees C. So we can increase boiling point by increasing our atmospheric pressure or by increasing the pressure inside of a container through sealing it up and allowing the pressure to increase. And so we can change pressure by using things like vacuum pumps. We can change pressure also by going to higher elevation. So if you go to higher elevation, you probably either have done this if you've been at high elevation, notice that cooking times are longer, or if you're looking at a recipe, it might say at elevation you have to cook longer. It's because at high elevation, your temperature of water is going to boil at a little bit of a lower temperature. It's going to take food longer to cook at a lower temperature. If you can then likewise throw it into an Instant Pot or a pressure cooker, you're going to add to the pressure, and you're going to increase the boiling point of water, so food's going to cook faster because water is boiling at a faster temperature. If a pot is maintained at a temperature of 100 degrees C, takes an hour to cook, let's say. If you have the pot at 110 degrees C, because water is boiling now at a higher temperature, it's going to cook faster. And so we can change boiling point by changing the applied pressure. We can change the applied pressure through sealing a container, or by using a vacuum pump, or by maybe changing our elevation level. Okay, so which substance below do we think would have the lowest vapor pressure at room temperature? So let me throw this to you guys. Think about whether lowest vapor pressure should have the strongest intermolecular forces or the weakest intermolecular forces, and then try to figure out which compound coincides with that. right, so lowest vapor pressure should be the one that has the strongest intermolecular forces. We increase those intermolecular forces is going to be the way that we hold the liquid together, not allowing it to escape into its vapor phase. And so then likewise, the highest vapor pressure will be the one with the weakest intermolecular forces. So we want the weakest intermolecular forces, and so pentane here, being the one that only has dispersion forces, ethanol has hydrogen bonding forces, ethylene glycol has more hydrogen bonding forces, glycerol even more hydrogen bonding forces, pentane no hydrogen bonding forces. It's going to have the weakest intermolecular force. This would have the highest vapor pressure. The lowest vapor pressure we would expect to be the one with 3 hydrogen bonding groups instead of just 2 or 1. So we saw previously in the last slide that having ethylene glycol increased its boiling point, decreased its vapor pressure. Glycerol is going to do that even better with the 3rd hydrogen bonding group. Interestingly, I think ethylene glycol and glycerol probably both have near 0 vapor pressures at room temperature, so neither one of them probably have much of a vapor pressure at all. But if ethylene glycol had a little bit of a vapor pressure, we would expect glycerol to be even lower. And so having that 3rd hydroxyl group allows it to form 3 hydrogen bonds, giving it a much stronger set of intermolecular forces, therefore a lower vapor pressure. And so one of the last topics in the chapter is phase change diagrams. And so what a phase change diagram is showing us is at what pressures and temperatures does a sample exist as a solid, liquid, gas, and then even something we might call a supercritical fluid. A supercritical fluid was something I was mentioning in the last chapter. When you imagine having a relatively high pressure of a gas, say in a cylinder, it really starts to be described better as a supercritical fluid, something that kind of begins to have a blended set of properties between a gas and a liquid. And so we reach a point at which the critical point where we're above the critical temperature, critical pressure, we would just call that substance to be a critical fluid at that point. And this isn't really all that exciting. It doesn't mean it explodes or does anything crazy. It just means it has the properties of a gas and a liquid. I used to have a slide on it, but CO2 is supercritical. If you increase the pressure of a CO2 sample, it kind of allows the gas to behave like a solvent. And so supercritical CO2 has been used in industrial applications to do things like remove caffeine from coffee. You take like solid coffee grounds, you can remove some of the caffeine. It turns out you remove other things too, because I think we all know decaffeinated coffee doesn't taste very good. But supercritical CO2 is actually something that's been used to remove caffeine from coffee and from tea. So then we have our liquid phase in the middle, but there's another interesting point, that's the triple point. A triple point is, it's the coexistence point between the solid, liquid, and gas, but it's also an interesting point because if we go below the temperature of the critical point, we're now either in the solid or gas form. So if you know the critical point of a substance, if you go to a lower temperature, lower pressure, the only phase change transition will be between the solid and the gas phase. And so that's our sublimation and deposition phase changes. And so for example, dry ice has a critical point at about negative 56 degrees C and well above atmospheric pressure 5 atm. And so what this means for CO2 is if you take it to a pressure, say at standard atmospheric pressure that's lower, then the only phase change for now a solid piece of CO2 would be the direct transformation into gaseous CO2. So if you've ever wondered, why is it that if you take dry ice, CO2, frozen, why doesn't it melt into a liquid like most other solids do? And it has all to do with where its where its triple point is. And so at 1 atm for CO2, the only phase change possible is the direct transformation from solid to gas. So for CO2, solid at 1 atm, the only phase change possible is into the gaseous state. And so there's no liquid phase at that pressure in between the solid and the gas. And so if we imagine something like water, water at 1 atm does have the normal transition into a liquid phase, and then that liquid phase into the gas phase. And so that's because for water here, this is our diagram for water. For water, its critical temperature and pressure are about 0 degrees C and a really low pressure, like less than 0.01 atm. And so as long as we're at a pressure above this critical pressure, then liquid water can have the process of going from solid to liquid to gas. If we reduce the pressure, if we take a piece of ice, put it in a vacuum chamber, reduce the pressure, then we will eventually see, if we increase the temperature of the water sample, we'll see it directly transitioning just like dry ice does, from solid to gas form without ever hitting the liquid phase. And so if we reduce the pressure, then we could have the direct solid to gas transitions. And so then we also have a critical temperature of water, pretty high temperature. So notice over 350 degrees C, really high pressure. So for water, it's not behaving as a supercritical fluid until we reach a pretty high temperature and pressure. Notice for CO2, it's at a more reasonable temperature and pressure. It's closer to room temperature, lower pressure. We'll see on a slide that kind of compares some critical temperatures for some different substances that we'll see the critical points are also related to intermolecular forces. You strengthen intermolecular forces, you increase your critical temperature and your critical pressures. One other thing worth pointing out for water versus say CO2 and most other substances is this curve here, whether or not it has a negative slope or a positive slope. What this would mean here for water, it might be hard to see, let me zoom in a little bit, is if you notice water, if I take water right about here where it's a liquid, let me actually put it closer to standard atmospheric pressure, close to 1 atm. So we have a normal sample of water at like 0 or close to 0 degrees C. So imagine water at like 1 degree C or 2 degrees C. For most samples, if you imagine CO2 in a similar range of its diagram, if I take this sample of liquid CO2 at a pretty high pressure, again, because its critical, or its triple point pressure was pretty high. So we're already at a pretty high pressure. If I continue to apply a pressure to CO2, it eventually will solidify. So if you take a liquid and you push the particles closer together, most substances you're pushing it closer to being a solid. But for water, it actually does the opposite. If I take water as a liquid and apply pressure, it stays liquid. So this is applying pressure. So we apply pressure to liquid water, it stays liquid. In fact, I can go to a point where I have solid water, and then I can apply a pressure and it's going to turn into liquid water. And this all has to do with density. So I think we all know the density of ice is lower than that of liquid water. And the implication there is if you actually take solid ice and you physically apply a pressure to it, you can melt the substance. You can melt ice by applying pressure. So, and that's because ice has a lower density compared to water that's liquid. And so if you take a solid that has this property, then you can apply a pressure and then you can turn the substance from solid into liquid. And this is very abnormal. Very few substances have this property. Water is very unique in this regard. So most substances, if you take the liquid and you press it together, you're pushing the particles closer together, you're going to freeze them out in the process. And so water has this negative melting point curve associated with it. We also then see this curve here is the kind of the same kind of curve we were seeing for our vapor pressure curve. So this is our vapor pressure curve between our liquid and our gas form. So this looks very similar to a curve we were looking at before. So this point to here is our vapor pressure curve. I lost the ability to write. But it's the vapor pressure curve like we were seeing a couple slides back. So it kind of has that bend to it like we were seeing before. And so that's just showing us in the transition between our liquid and gas sample. And so our vapor pressure diagram is trying to show us that the ranges of temperature and pressure, where does the substance exist as a solid versus gas versus a liquid. And so solid at low temperatures, low pressures, more liquid at higher temperatures, higher pressures, and then gas at higher temperatures, but still also at lower pressures. So this is the slide I mentioned that we're going to compare some critical points, or some critical temperatures and pressures. Remember, this just means above these temperatures and pressures, the gas would start to behave like a liquid too. And so if you go above the critical temperature and pressure, you just have a blended set of properties of the substance. It just starts to behave like a gas and a liquid. So it starts to take on properties of both a gas and a liquid. So nitrogen, relatively low critical temperature and pressure. As you increase the size to argon, you increase the critical temperature and pressure a little bit. Same to O2, a little bit bigger, a little bit higher critical temperature. If you go to like a bigger molecule, CO2, you increase the critical temperature and pressure. If you go to things that start to hydrogen bond and have stronger intermolecular forces, you're increasing the critical temperature and pressure. And so the critical temperature and pressure, these values here, are directly proportional to strengths of intermolecular forces. You strengthen the intermolecular force, you then allow the gas to exist as a gas to a higher pressure and higher temperature. So critical temperature and pressure just also then related to intermolecular force strengths. Okay, the last slide, there's not much in the final section of the chapter that we're going to cover, but there's just one picture I really like talking about because it tells us how soaps and detergents work. And so a soap has a group on it that looks something like this. It has a C double bond O. This looks like acetic acid when we lose the H plus, like the acetate ion, but where we just have a long chain of carbon atoms attached to something that has an ion, and then we get this ion dipole force of attraction. So if you've ever seen like the sodium lauryl sulfates or whatever, these are different sort of groups that have a charge where you get a strong attractive force between this ion and water. You get that strong ion dipole force. And then the long chain, you use a really long chain because it really starts to attract grease particles and oil particles. And so you can create a solubilized droplet by having a long chain of carbon atoms that dissolve oils and droplets, things that are nonpolar, and then solubilize the chain by having then all these strong ion dipole forces where water is really attracted on the outside of the force. And so I just wanted to show this is how detergents are working by having a long chain of carbon atoms and then the strong ion dipole force of attraction to have a water attraction end, and then a hydrophobic chain where this chain here doesn't really like water. It likes the oil droplet, but we make a droplet out of this. And so this is how a grease particle becomes solubilized and go down the drain. And so I just thought I would show how soaps work here at the end of chapter 11. So we'll look at solids in chapter 12 briefly and then get into some review topics on Friday. All right, guys, thanks for your attention. Have a great day.